Hi everyone. Today I'm going to be presenting this paper. Uh, Roster, um, Roster. Frozen Clip is a strong feature for open vocabulary action recognition. So it was published in Iclr 2024 from HKU and Baidu. Basically what they do in this paper is they introduce a framework called Roster, which is a open vocabulary action recognition framework which leverages the clip model. Uh, it's much more generalizable than the other models. The challenge it solves is normally clip is for image data. So they extend the clip model for video, for understanding video. And also normally when we train one model for one particular data set, it gets too overfitted to that one particular data set. So they also teach something which make the model more generalizable for all datasets. So what is open vocabulary? So in this context of this paper, open vocabulary means the ability to recognize action categories that may not have been seen during training. So in the training, the classes are available, might not be available in testing phase. So yeah, this means the model can understand and classify actions beyond fixed and predefined set of categories, allowing it to generalize and identify actions in videos, even if those specific actions were not a part of the dataset it's originally trained on. So basically, what I said earlier, the model can work on the testing sets which is not available in training phase. What happened in the previous works. They compared it with few previous works, the original frozen clip, the action clip, which is another action recognition clip models, AIM and ST adapter. All of them are uh, action recognition models using clip. And they also have tested it on these three datasets, on which the models weren't trained. All of these models were first trained on kinetics 400 datasets and were tested in these datasets to test how does it perform if it's not trained on that specific dataset. So, and these uh, numbers in the bracket means how similar are how similar is the dataset to that particular dataset. It means K400 dataset. So that if the value is higher, it means the dataset is more similar to K400 dataset. And if the value is less, it means the similarity is less between kinetics 600, let's say, and kinetics 400 dataset. So if the value is less, it's less similar. If the value is higher, it's more similar. So what happens in summary of this graph is if we use just frozen clip and train it on kinetics 400 dataset, it performs the worst of all uh, action model in the dataset if it's untrained. Also for action clip, it's better, but no, not great. So, but if they freeze the clipper and use ensembled output of clip and the output of clip here, output of action clip model there, then the accuracy improves. So what it means is the clip, the pre-trained clip to begin with is much more generalizable than if we train it on a particular data set. So the motivation came from there. So when we tune one model for one particular data set, we have to tune it in a way that we can keep the generalizability of the model after training. So why do we use language model in our vision tasks? Philosophically speaking, the purpose of using language model to make the model more generalizable. So if it's trained for one particular task, it should not just be specific for one particular data set. It should be working for in the wild. So like Clip, the Clip works for almost everything nowadays. So these are the two most desired properties of vision language models. So the Clip model should be a vision language model for action recognition specifically. So the Clip model should require video specific knowledge to bridge the gap between image and videos. So as we know, the Clip is originally trained for image, but we have to extend it to video, so to understand video better. So to understand temporal and others, it's written there. So, and next thing is when we extend it to extend the video through one particular data set, it also should preserve the strong generalization of capability of Clip. So the way they do it here, they use a distillation method. So basic idea here is they have two models, one teacher model, one student model. So the teacher model is fixed, and the student model is trained for one particular data set. And I'll go into much more details what this residual feature distillation is. But basically, you can think of it as some sort of MSC loss in using some residual technique, residual adding technique, to force the student model to not be vastly different than the teacher model. So in this paper, they have two components. The first, they fine-tuned one model to bridge the gap between image and video tasks, and also knowledge distillation method to maintain the generalizability of pre-trained Clip. So let's see how do they do the action recognition part. So let's say we have a video xi, and we have, let's say, t frames there. In video, there are t frames. That means there are t images in the video. So then we input all the frames to Clip's image encoder, and we get the image embeddings of each frames. So that's the embedding of all frames together. So how do we convert it to video? So to convert it to the embedding of video, they just do simple average pooling from all the frames and make it the final vector of image and video embedding. So they first get the image embeddings, all image embeddings from all T frames using the image encoder, and then they do simple average pooling on those embeddings of image. Next, for text input, it's same as the image Clip. So they just put some text for the template. They show they put a video of something, let's say clapping hand or playing something or something. So then they augment this input using GPT 3.5. So they first say they ask GPT to make a video description of this scene. So then GPT 3.5 makes description of that particular scene, and then they use that text to put it on the text encoder and get the text embedding. Later, they use the typical contrastive loss of Clip for that particular video. So we have video embeddings, text embedding, and now it's like original Clip. So they can train train it in contrastive method and make the Clip model. So next part is feature distillation. For feature distillation, there could be three methods. So let's say this is teacher model and this is student model. And this is after inputting the text and image, we can get the embeddings from both. So for teacher embedding, teacher's models embedding and student models embedding. So we can directly apply L2 loss here. This LFD is just L2 loss. So if you just apply L2 loss, that's one way of feature distillation. Another way of feature distillation is we could project the student model's output to a space, also teacher's model output to a space, using something like MLP or something to project something to some embedding to another embedding, some space to another space, and perform loss there. And then third way is using the residual. So we'll define a network which will find the difference between teacher's model embedding and student's model embedding, and force the student model to be similar to the teacher's model. Each three methods has their own benefit and demerits. So the good thing about this part is it's direct. We don't have to project using MLP or something. But the problem here is if we do it like this, if we just use L2 loss on student models embedding and teachers models embedding, the flexibility of student model is much less to be fine-tuned to a particular data set compared to teacher model, because we are forcing it to be exactly same as teacher model, so it cannot be fine-tuned. And if you use MLP, another problem there is that we cannot use different kind of clip models. So the size of embeddings here, that's the embedding size of student model and a teacher model also will have to be same. But since we are just doing L2 loss here, they cannot be different. So the size also have to be same. But so if we want to use two different teacher model kind and student model, so let's say this teacher model is not exactly similar to student model, so the embedding space is different. So we can project the embedding students embedding to teachers embedding space, and using MLP or something, and use L2 loss. Problem here is if we use the loss in this way, the distillation guidance is too vague. So it can work, but the distillation is not, knowledge distillation is not very strong in this method. So combining these two, they find in this paper, they proposed another method. They will find they propose the residual network, which will find the difference between teacher model and student model, and add the difference to the student embedding sub. So then they combine the residual and the output of student embedding and do the rest. This could be defined as like here. So here, ZG is the output of student embedding, and this part here, they defined it as a residual network where W1 is a MLP layer, sigma is a gallery activation, and W2 is another MLP layer. They use two MLP layers to find the residual between teacher's model embedding and student model embedding. So the benefit they say here is, first benefit they say, since they're just adding the residual to the student's embedding, they are not forcing the student model's output to be teacher's model output. So the student's model's output can be a bit different to from the teacher's model output. So there is a scope of fine-tuning of student model to a particular data set. And the next one here, they say, is the alpha factor. So if the alpha means to what extent you want to force your student model to be similar to teacher's model. So if alpha is high, if alpha is big, then the student model will be much more similar to the teacher's model, and if alpha is small, then the student model will be less similar to the teacher's model. So in their experiment, they say if they use a small number for alpha, let's say 0.1, it leads to better performance than the large one. This phenomenon suggests that pre-trained clip is already possessing strong representation, so they just slightly adjust the student model from the teacher model. Uh, so basically what means is student model is more or less generalized. Let's say in the example here, even if the action clip or other models weren't particularly trained on this data set, it was performing not bad. It's 77.4 in that particular data set. So like it's not that bad. They just need to like tune it a bit slightly to get better performance. And the third portion is here. What they say is they initialize this W2 the last MLP layer is 0. So what it does is when the training is starting, the whole portion, the value of this part is 0. So it doesn't add anything in the beginning of the training. So once the model starts training, the value of this W2 changes accordingly. So the training, the student model updates according to the residual based on the change. Based on the change happens during training. They say if they initialize like that by initiating a W2 as 0, the training stays much more stable. So this is the overall loss function after doing everything there. So they do the loss for L2 loss for visual encoder from using the teacher models output and the students model output, also the text encoders output, and from teacher and student. They add both together, and for the final loss function, they use those the contrastive loss from previous here, this portion here, this contrastive loss here, and also this distillation loss. And this pattern is coefficient. We can tune it as we need for our particular task. So for the experiment, the experiment is in two settings, or one setting is based on novel. The based on novel means they use same dataset for testing, but the classes in training and testing are different. They're not the same classes. They're from the same dataset, but they're not the same classes. And another setting is cross dataset. Cross dataset means they trained the model on one particular dataset and tested it on different datasets. These are the experiment result. So they in a based on novel training and testing, so they show their model outperforms all the existing models here. So and pretty much in all datasets. So one more thing, in their action recognition section here, so this is actual recognition model. They don't propose anything new. They just use existing model. They just show that distillation method works and makes the model more generalizable. So in this experiment here, they used V-clip. This V-clip. V-clip here. It's not shown here, but they use V-clip as that action recognition model and use that distillation training technique to make it more generalizable. So in this method too, I guess they used V-clip for this setting, and their distillation method outperforms the previous existing pretty much in all data in based on novel settings. So when they do train it for when they test it for cross dataset, they also show their model outperforms all the existing technique for this distillation and cross dataset settings. They also show their model can be used using any model, so it doesn't have to be weekly. So even if they use just clip, the original clip, and just using that distillation method, it improves the performance in all settings. Also, reaction clip, V clip, all pretty much in all settings. If they use that distillation method, the student model get much more generalizable compared to the existing model. And this is the effect of their proposals. So if they use if they just use L2 loss between students models embedding and teachers model embedding, it performs worse. If they use MLP, it performs a bit better. But if they use the residual law, residual settings, residual feature distillation settings, it performs best. So both for text and both for visual model and text model, if they combine both, the result is the best. And yeah, that was it for me. If you have a question.